Mario 64 is one of the most dissected games of all time. It's been studied, speedrunned, and analyzed for decades. At this point, we basically know everything about it. So instead of going over the same stuff again, I thought, why not try a different approach? What if we applied quantum mechanics to Super Mario 64? Now, before we dive into the weird effects that would happen, let's set some goals for this experiment. If we could somehow turn the console quantum, what could we actually try doing with it? Well, for starters, beat the game normally. Beat the game without pressing the A button, the ABC challenge. And maybe even speedrun it. But before any of that can happen, we need to figure out how to actually turn Mario 64 into a quantum system. Here's the deal. We measure how quantum something is by its decoherence. The bigger the decoherence, the more it behaves classically. Things that constantly interact with the environment, like the moon or even us, barely follow quantum rules because of gravity, light, temperature, and all that. So, to make the console quantum enough, we need to reduce its interactions with the environment. Basically, hyper-isolating it. We'd put it in an almost perfect vacuum and cool it down until its thermal energy is close to absolute zero. At that point, the electronic components inside the Nintendo 64 would start behaving quantum mechanically on a macroscopic level, completely changing how the console's logic works. Instead of following predictable, deterministic rules, the N64 would start obeying the strange, probabilistic laws of quantum physics. And that's when things get really interesting. Alright, so now that we've turned the Nintendo 64 into a literal quantum object, it's frozen, isolated, and basically ignoring the rest of the universe. Let's see what would actually happen if someone tried to play Mario 64 like this. Okay, let's start with the normal playthrough. Since we're talking about probabilistic laws here, let's go through the possible scenarios and figure out the most efficient ways to beat them. At first, you'd probably just press start and jump into the game. But here's the catch. Every button on your controller has two states, pressed and not pressed. Except, in a quantum system, pressing the button doesn't actually send a clear signal to the console. Instead, it sends out a probability wave of electrons. There's only a chance the button actually does something. We can describe that chance using this equation. P jump equals 1 minus d times s plus d times a, where d is the decoherence level, basically how classical or noisy the circuit is. S is the state of the button being pressed, and a is the action that actually happens. If we consider perfect conditions where decoherence splits everything evenly, the final probability comes out to exactly 50%, meaning every button you press only has a 50-50 chance of doing what you intended. So yeah, it's technically possible to beat Mario 64 while the console's under quantum rules. It's just a little tricky. After all, you've only got a 50% chance every time you touch the controller, right? Remember when I said there are only two possible states? Pressed and not pressed? Yeah, I lied. In quantum mechanics, those aren't simple binary states. They're actually vectors in a two-dimensional Hilbert space. What this means is that there are way more than just two possible states for a button. The button can be pressed and not pressed at the same time, or it can trigger what I call a double pulse, where one press is counted twice. Sometimes it can even create a glitched pulse, where another random input gets executed instead of the one you meant to press. Basically, there are infinitely many possible outcomes every time you touch a button. We can describe this whole thing mathematically with a single equation. Psi equals the sum of each possible state, multiplied by its probability amplitude. In other words, the controller exists as a cloud of probabilities. The game doesn't actually happen until you observe it. When that happens, all those probabilities collapse into one reality on your screen, chosen at random. But here's the funny part. Even though this makes the game way more unpredictable, it also makes the No A button challenge technically possible. You don't need to press A anymore, you just need to hope that quantum randomness picks the right universe where Mario decides to jump on his own. So yeah, you can beat Quantum Mario 64 without ever pressing the A button. You'll just need a lot of wave function luck. Now let's go deeper. The Quantum Speedrun. In normal Mario 64 runs, the timer starts when you turn on the console. But in a quantum world, things get weird. The data that stores Mario's position, his health, and even his stars are no longer bits. They're qubits. Each qubit can exist in a superposition, written like this. Psi equals alpha times 0 plus beta times 1. The squared magnitudes of alpha and beta give the probabilities of being 0 or 1. If we assume a perfect system, every qubit starts in a half 0, half 1 state, a perfect 50-50 superposition. But quantum waves don't just add, they interfere. That means your button presses and game states interact with each other, creating constructive or destructive interference. So now, this isn't about reflexes or frame-perfect tricks anymore, and it's about wave function manipulation. If we want the beaten game universe to appear, we need to amplify the amplitude psi that multiplies that state, until it's as close to 1 as possible. Basically, we want to make the winning universe the most probable one. And that's where Grover's algorithm comes in. A real quantum computing trick that lets you find the correct result faster than any classical method. It uses two main operations, the oracle and the diffusion operator. The oracle marks the correct solution, in this case the game-beaten state, by flipping its phase in the quantum state vector. Then, the diffusion operator amplifies that state by reflecting all the other amplitudes around the mean. Imagine it like a ball rolling around a sphere. Each spin tilts it closer to the direction of victory. After a few rotations, the ball perfectly aligns with the winning state. Once that happens, the probability of the game-beaten universe approaches 1. So when you finally observe the system, it collapses directly into the timeline where the game is already finished. That means you technically beat Mario 64 before even pressing start. Retrocausality in action. The game was already complete before time began. And just like that, we've done the impossible. A negative time speedrun. So what does a negative time speedrun even mean? Well, in the quantum realm, time doesn't really flow the way we're used to. When you manipulate a system's wave function just right, information doesn't just move forward, like it echoes backward. That's retrocausality. Your inputs don't wait for the future to happen. They create it, and then rewrite the past to make it consistent. So when you power on the console, it's not really starting the game. It's just observing a reality where the game has already been completed. Mario, Peach, Bowser, every atom in the system already knows the outcome before you even touch the controller. Your act of pressing start isn't the beginning. It's the confirmation. Inside the console, all the quantum states that once described possible playthroughs collapse into one, the victory state. The game doesn't load, it resolves. The stars are collected, Bowser is defeated, and the credits roll from a timeline that technically hasn't happened yet. And when the screen fades to black, the timer doesn't read 0. It reads a negative time. So, yeah, negative time speedruns are real.